Hello together. Today I want to explain the Smith chart. The Smith chart was already developed by Phillip Smith in 1939, and what I want to do today is I want to explain how the Smith chart is created. So in the first step we will have here a look to the difference plane which are involved by the development of the Smith chart. We have here the normalized set plane, and as normalizing impedance is always, in most cases, is used the characteristic impedance of the transmission line we consider. So if I have a set plane, this means I have a real value and a complex value of the set plane. So we have here the real axis of the set plane, and here we have the imaginary axis of the set plane, and here we have the value 1, which means this is the characteristic impedance. Normally the characteristic impedance is assumed to be real. Here we have the short circuit, a zero impedance, and here we have J and minus J. And all impedances in this impedance plane are now mapped onto the R plane. Here we have the R plane, which is the plane of the complex reflection coefficient. Also what we have here, we have the real part and the imaginary part, and we have here certain values. For example, here we have a -1, which means we have here a short circuit. Here we have a +1, which means we have an open circuit, and here we have J and minus J. And what I want to do now is to show you how we can map now certain elements from the set plane onto the R plane. The mapping is done with the help of this relation here, which describes how the set values are mapped onto the R plane. This equation describes this mapping process. And in the first step, I want to have a look to the set, to all impedances with a real part of 0, which means we will first map this imaginary line here. And to do this, I can now tick here, and you see here we have the imaginary line, which means here we have always the real part of the impedance is 0, and especially here we have the short circuit. And this line is now mapped onto the unit circle in the R plane. So all impedances lying in the right half plane of the set plane will be mapped into the unit circle in the R plane. And especially here you see now that this point is now described by its impedance. Here we have the impedance 0, which corresponds to a reflection coefficient of -1. But later in the Smith chart you will not see this -1 anymore, but only we will see the 0. And we can go on in the mapping. So I here mapped, for example, the total line with a real part of normalized real part of 0.2. And this is mapped into the unit circle on this circle here. You will see that always a circle is mapped into a circle where we can say a circle or a straight line is nothing else but the circle with an infinite radius. So we can now go on in the mapping. So you have here all resistances with a real part of 0.5. The real part is constant, but the imaginary part will change. What I did, of course, here is cannot extend this to infinity, but here in the Smith chart it's a fine thing that all the impedances now are mapped into the unit circle. Next we can have a look to a very important circle in the Smith chart. This is the one circle, which means on this circle we have the real part 1, and this is mapped onto this circle here, which again means on this circle we have always the real part 1, but a changing imaginary part. This is the so-called one circle. And of course we can go on in the mapping, and that of course I will not map now all, or I cannot map all impedances here from the Z plane onto the R plane, otherwise you will not see anything anymore. And the blue lines I will call now real part circle. So here these are all real part circle, and it's very important that you can recognize the circles as the real part circle. And beside this real part circles in the Smith chart we also have the imaginary part circles. So I did this now in one step. So we have here now the all impedances with a impedance of J 0.2, J 0.5, and so on. And these lines, coordinate lines of the Z plane, are now also mapped into the R plane. And what you see here now is, you see now the structure of the Smith chart. And in the next step, perhaps before I go to the next step, I explain here we always have a positive imaginary part, which means these are all impedances in this part of the Smith chart, like all the impedances with a positive imaginary part, which means these impedances have an inductive part. And in the next step we will now map also the capacitive parts. So as soon as I consider an impedance with a negative real part, imaginary part, then we have the capacitive values, and these capacitive values are all mapped in the lower part of our Smith chart. And what you see here now in total is in principle the Smith chart, but in a real Smith chart always these coordinate lines of the R plane are missing. And also this number is missing, and this number is missing, and also this number is missing. This number here, you see, if I have the real part, if I have an impedance with a real part of 1, then its reflection coefficient is just 0. So, but in the real Smith chart you will only see this 1. But you must remember that in this case here we have a 0 reflection coefficient. And if I want to calculate now a reflection coefficient, I just go into the Smith chart and tick, for example, here we can have a look, for example, if I would have a real part of 1 and an imaginary part of j, 2, then I can tick this cross here, and then the length from this point to the origin of the coordinate system, this will give us the length or the value of the reflection coefficient. And now you can also measure the angle of the reflection coefficient. But this I want to show you with the help of another program. Thank you for watching this video. Your comments are welcome. Please join again.